Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
So in this video, we're going to talk about the substitution rule and how it makes it simple to help us with integration. Now, keep in mind that this is kind of like working backwards through the chain rule. So when you derived, you chain ruled it. So when we're going backwards, we have to substitute rule it. So let's look at this particular example. This is a solution that we would have found after we had done a chain rule where we did the, power rule, and then we might have multiplied by the derivative of what's inside. So right now, our only way to do this would be to go ahead and FOIL this out and then multiply by x. So that would be x to the 4th, so x to the 5th. It'd be 2x squared, so 2x cubed. And then it'd be plus 1, so plus x dx. Okay. And if I integrate that, I'd have 1/6 x to the 6th plus 2x to the 4th over 4 plus x to the 2nd over 2 plus c, or 1/6 x to the 6th plus 1/2 x to the 4th plus 1/2 x squared plus c. Okay, and that works great, but not everything am I going to be able to do that with. So what the substitution rule says is, all right, we're going to change the variable. And they normally use u. So we're going to let u equal x squared plus 1. And therefore, because u is that, the derivative of u is 2x dx. So see, I'm using that implicit differentiation. Okay, now I kind of have this like this is my u, but that's not my du. So let's rewrite things a little bit differently, okay? One half du would equal x dx though, right? Okay. So the integral of x squared plus 1 squared multiplied by x dx. So see how I just took what was there in the original problem and I reordered it and I color coded it. So now I can substitute u squared and 1/2 du. So just direct substitution. Now, are there some people that say to put a times 2 times 1/2 out here because now we're technically multiplying by 1? Yes, there are people who say that. And then it does match your du perfectly and you'll have a 1/2 out front, but the way I did it, we can also pull a 1/2 out front. So do you want to do perfect substitution or do you want to multiply by 1 so that then you can do multiple perfect substitution? It's up to you. Either way, we should be looking at 1/2 integral of u squared du, and now I can apply the power rule. That will give me 1/2 u to the 3rd over 3 plus c. So when I resubstitute back in, I get 1/6 x squared plus 1 to the 3rd plus c. Okay, so is that the same thing? Well, let's check it out. 1/6, I'm using Pascal's triangle, so it'd be the first thing cubed. So plus 3 the x to the 4th plus 3x to the 2nd plus 1 plus c. So 1/6 x to the 6th plus 1/2 x to the 4th plus 1/2 x squared plus 1/6 plus c. Is that the same thing? Yes, yes, yes. could those constants be equal? Absolutely, yes, it's the same thing. But one is going to help us reverse that chain rule. Okay, so you're going to again have to decide which equation is inside of what. So we have to let something equal u. So we're going to have the integration of f of g of x times the derivative of g dx is going to equal the f of u du. And you'll let u equal your g of x, and therefore your du will be your g prime of x dx. So g of x, that's our u, du is right there. Okay, so sometimes I do the rule where I move the 2 over and make it times 1/2, like I did here. Sometimes I will do the times 2 times 1/2 rule. It just depends on how I'm feeling in the moment. They're both actually the same thing. It's just different ways to look at, you took a right-handed corner or you turned 90 degrees, same thing, right? So best answer, and the nice thing about these answers is they're already in factored form, so that's pretty cool. Okay, so really every one of these problems is going to look different. The best way to do this is just to start powering through a bunch of them and really understanding the difference between your u and your du. So x cubed multiplied by cosine of x to the 4th plus 2 dx. Now, usually when you have a trig word and it's a single trig word or something, it's pretty easy to figure out your u. This is going to be your u. So our du is 4x cubed dx. And we only see that x cubed dx there. So technically, 1/4 du is going to be that x cubed dx, x cubed dx. Okay? So now I'm going to substitute. 1/4 du will take care of what's underlined in green, and cosine of what's underlined in blue. Okay, so I know cosine is the derivative of sine, so when I integrate, I go back to sine plus c, and then of course I have to write it in proper form, 1/4 sine of x to the 4th plus 2 plus c. And that's our final answer. So make sure you remember to resubstitute your u value in indefinite integrals. Definite integrals, we can play around, we can do a couple things extra, but we haven't got to that part yet. Okay. So this one I'm going to use the other method of substitution where I times. Instead of adjusting my du, I'm going to adjust the problem. So first of all, I'm going to write the problem as okay, wow, that's blurry again. Okay, so I'm going to let u equal 2x plus 1. So du will be 2 dx. So I need a 2 here, so I'm going to put a 1/2 here. So that quote-unquote is multiplying by 1. So 1/2 the integral of the square root of u du. I got to put that in power form. 1/2 the integral of u to the negative 1, or positive 1/2, sorry, du. So I'm going to add 1 to that. 1/2 u to the 3/2 over 3/2 plus c. Now remember, dividing by 3/2 is the same thing as multiplying by 2/3. So I could either get 2/6 or I could get 1/3. So 1/3 u to the 3/2 plus c, and my u value is 2x plus 1. Whew. Okay. I encourage you to pause this video for a second after I get the problem written down and think about what your U value should be for it. And I'm going to go ahead and rewrite it. Okay, so we have a denominator, and the whole denominator could be our U, or just what's inside that radical once I rewrote it in negative exponent form. And if you just said the 1 minus 4x squared, that is your best U. So your du is negative 8 dx. So if you like doing the times negative 8 times negative 1/8, that's the same thing, right? Because if you multiply those two light blue things together, they will multiply to positive 1, and we can always multiply anything by 1 without changing it. So it gives us negative 1/8, integral of u to the negative 1/2 du. So now I'm finally going to integrate negative 1/8 u to the 1/2 over 1/2 plus c. Dividing by 1/2 is the same thing as multiplying by 2 over 1. So I get negative 1/4 u to the 1/2 plus c is my final answer. And replacing that u. And you could write that in square root form as well. Okay, so we're just going to keep doing examples. Pause the video every time I write one down. See if you can try it before me. See what you're thinking the u is in the du. That's going to be the hardest part of these, is figuring out what should my u be, what should my du be. Integral of e to the 5x dx. Okay. My rule for e is e to the u, so my u is going to be 5x. My du is going to be 5 dx. 5 1/5. I'm just feeling this method better tonight. All right, so I'm integrating 1/5 integral of e to the u du, which integrates to e to the u plus c. So my final answer is 1/5 e to the 5x plus c. And we can see that we're really reversing that chain rule process. So that's what all this is taking care of, is that chain rule. All right, now we're going to get creative. And that's sometimes what this is about your creativity. So I have the integral of 1 plus x squared multiplied by x to the 5th dx. Okay, my u has to be 1 plus x squared because that's what's inside something else. So my du has to be 2x dx. Uh-oh. Well, I can write it that way, and then I'd have a 2 and a 1/2, which would take care of this and would take care of that. But I still have that thing. So I'm sitting at 1/2 integral u to the 1/2 times x to the 4th times du. Yuck, I need all x's. I can't have this mixed variable thing going on because I can't integrate that way. What do I do? Well, hope is not lost. And it might feel like hope is lost, but let's play a little bit. If u is going to be 1 plus x squared, then u minus 1 would be x squared. And if I squared both sides, I get this, which is what I have right there, which I know it doesn't look any better, but hear me out. We could actually FOIL that out and get mu squared minus 2 mu plus 1. So then we have the 1/2 integral u to the 1/2 mu squared minus 2 mu plus 1 d mu. But now that's something I can actually distribute. We're over there, 1/2, right? U to the 5/2 minus 2 mu to the 3/2 plus mu to the 1/2. Now it's finally something I can apply the power rule to. So I had to keep playing with my substitution until I got to somewhere I could apply a power rule. That's basically what I'm doing. I have to be able to apply one of those simple rules. Okay, so 1/2 times u to the 7/2 over 7/2 minus 2 mu to the 5/2 over 5/2 plus mu to the 3/2. And I am saying mu because technically I'm using the Greek letter mu, mu, mu. And of course our plus c. Okay, so 1/2 times 2/7 mu to the 7/2 minus 2 times 2 over 5 mu to the 5/2 plus 2/3 mu to the 3/2 plus c. All right, so I'm going to have a final answer of 1/7. Mu is 1 plus x squared minus 2/5 plus 1/3 plus c. So making sure we keep substituting directly for what mu is. And we got a little creative there. And creativity is not bad as long as we're doing proper substitution. And that's the big key there, is we just have to keep substituting the proper value or something equivalent. Okay. So while I know some of you probably have a rule for this next one memorized, we're just going to head and we're going to prove why it is what it is. So the integration of tangent of x dx. And you might be looking at it and going, that's not going to have you to, we have a rule. You're right, we do. But why do we have that rule? Well, we know tangent is sine over cosine. Okay? And we generally, if we're going to have to pick one, we let the denominator equal our u. So du will be negative sine. So I'm going to make a negative and a negative. That'll make a positive, right? So now I have negative integral of 1 over cosine of x multiplied by negative sine of x dx. So that's negative integral of 1 over u du. And we have that rule for 1 over u, it's natural log plus c. So we get natural log of cosine of x. And that's why the rule for tangent is what it is. Now, just a couple reminders because you also might not see it written that way. With a natural log, a negative could go back up. So natural log of cosine of x to the negative 1 power, which is the same as natural log of 1 over cosine of x, which is the same thing as natural log of secant of x. So that's another reason why you might see that tangent integrates to the natural log of secant. So something to keep in mind, that we can rewrite these things with natural log in multiple ways due to the expansion of how natural log expands. So what if we have definite intervals? Because all of this I've done today have been with indefinite intervals. So what happens when we're trying to work with something like this? Okay. So we're going to have to start off with, there's two paths we could take. We'll just go with that. We could do it indefinite and then later put in, or we can adjust our bounds. We're either going to have to do it as indefinite or we're going to have to adjust our bounds. Okay, so the best way I think to do it is to actually just adjust your bounds. So if u equals 2x plus 1, then du is going to be 2x, or 2 dx. Now, x, u, we have 0 and 4. So mu would therefore be 1 and 9. Put a 2, put a 1/2. 1/2 interval from 1 to 9. U to the 1/2 du. Okay. Now over here, if you're doing it, you have 1/2 interval of u to 1/2 du, but we just don't have bounds on it. Okay, we're going to integrate this to, this would be 3/2 over 3/2 from 1 to 9. So we'll clean that up. That's the same as 2/3, so we'd have 1/3 u to the 3/2 from 1 to 9. Over here, you'd have 1/3 u to the 3/2 plus c. And so you'd say it's 1/3 2x plus 1 to the 3/2. And then you go from 0 to 4. Okay. Here we would just do 1/3 times 9 to the 3/2 minus 1/3 times 1 to the 3/2. Here you'd have to substitute 0 and 4 into this, and you would get 9 and 1. So why go back and put it back in? If you change it to u and you change your upper and lower bounds to u, and we're going for a numerical answer, you never have to change it back. Because again, we're looking for a numerical answer, not a variable answer. Okay, if you type this into the calculator, you get 26/3. So keeping it in U format, as long as you change your upper and lower bounds, is beautiful. That's what we want. That's all we have to do. Okay, so the integral from 1 to 2 of dx over 3 minus 5x quantity squared. And you might be tempted to FOIL this out, and you'd have to do long division. What I'm going to think of this as instead is 3 minus 5x to the negative second power dx. Okay, then I don't have quotients. U is 3 minus 5x, so du is going to be negative 5 dx. So multiply by negative 5, so multiply by negative 1/5. Make a little chart. 1 and 2, if I substitute 1, I get negative 2. If I substitute 2, 3 minus 10 is negative 7. Okay, so we have negative 1/5 integral. 1 becomes negative 2, 2 becomes negative 7. Of u to the negative second du. Now, if you don't like that your lower number is bigger than your upper number, it's fine, we can switch it. This is going to equal positive 1/5, negative 7 to negative 2. So anytime you need to flip your numbers, you're allowed to do that because subtracting in a different order changes your sign. Okay, so let's go ahead and integrate. 1/5 u to the -1 over -1 from -2 and -7. So we'll clean this up. -1 over 5u, -2, -7, 1/10 minus 1/35. And we get 1/14. Okay, so a couple of things I do want to point out. If you're getting stuck and you're having some issues with a few of your problems, you can always do a little bit of adjustments. Okay? If you know that your function is even, kind of like this, it's symmetric, right? You can just find this area right here on the right side from 0 to a, and then you can double it. And that's nice because then you're subtracting 0. If you can tell that it's perfectly symmetric, like it's an odd function, your integral is always going to be 0. And you can use that to your advantage as well. Long division might need to come in. There's a lot of different ways that we can adjust these equations to help us out. Let's say you have a polynomial like this. Now, it doesn't look like you're going to be using x minus 3 as your u-substitution, even though that's your denominator. And normally we would want our denominators are u. Instead, what we're going to have to do is we're going to have to come back to the world of algebra a little bit. Let's go ahead and let's just look at our polynomial. I'm going to use synthetic division, or Ruffini. 2, 5, 3, -4. Bring the 2 down. Times add, times add, 108, so 104. Okay, so we really have the integral of 2x squared plus 11x plus 36 plus 104 over x minus 3 dx. And if I write it out the full way properly, 2 integral x squared dx plus 11 integral x dx plus 36 integral dx plus 104 integral 1 over x minus 3 dx. Okay, and for these I can use just a basic rule. So 2 times x to the third over 3 plus 11 times x to the second over 2 plus 36 times x to the first, technically over 1, plus 104 integral, I'm going to let u equal x minus 3, therefore du will equal dx, 1 over u du. Okay, now I know how that integrates. That integrates to the natural log of u. Right? That's that rule. So our final answer for this would be 2/3 x cubed plus 11 halves x squared plus 36x plus 104 natural log of the absolute value of x minus 3 plus a big old C for the entire problem. So even if you need to get creative and rewrite these as a quotient plus a remainder, then that's absolutely what you should do. Just keep practicing these. The only way to get good at these is to practice them, just like with the chain rule you had to practice. And your U can be different every time. Now, I will say that these are ones where we're able to separate the variables. As you move into the end of Calc 1, beginning of Calc 2, you're going to start seeing x's and y's mixed together. And sometimes you're going to be able to move all your y's to the left and all your x's to the right and be able to integrate. But we're just not there yet with these videos. That video will eventually come. If you need it sooner rather than later, just drop a comment and I will get onto that. So otherwise, good luck with your calculus.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.